Welcome to this video lecture on testing a difference between means. Very often in statistics we are interested in two populations and whether they are different in some way. And if the mean is the parameter of interest, then we're interested to know, are the means the same or are they different? We'll begin with this example which involves paired samples. It is preferable, if possible, when comparing two populations, to use paired data. For example, what we're looking at here is the vitamin C concentration of peppers that are stored in the fridge and peppers that are stored at room temperature. Now, we don't simply take a random sample of different peppers in the fridge and then another random sample of peppers stored at room temperature, and maybe the types of peppers are different. Instead, every type of pepper that we store in the fridge, we also store at room temperature, and we'll compare them with each other. So we'll compare the green pepper stored in the fridge with the green pepper stored at room temperature, and so on. We don't use different items, we use the same items. For that reason, we call it a paired test. So this is an experiment carried out by Grace, who measured the vitamin C concentration of these peppers that were stored in the fridge and for the similar peppers stored at room temperature. We want to see if the storage condition makes any difference to the vitamin C concentration. So here in the data you see there's a green pepper stored in the fridge and a green pepper stored at room temperature. Likewise for a yellow pepper, an orange pepper and a red pepper. Now what we're going to do is we're going to look at the difference, whether the green pepper stored in the room temperature or the fridge had a higher vitamin C concentration. You can see there for the fridge it's higher than at room temperature. Then we'll move on to the yellow pepper and compare again. We will only compare the yellow pepper in the fridge with the yellow pepper stored at room temperature. We won't compare it with any other type of pepper. And again, you see, this is why we refer to this as a paired t-test. The data occur in pairs, and we are sympathetic to that in the way that we handle the data. So although we begin with what looks like two sets of data, the data for the fridge and the data for the room temperature, in fact, there's really just one set of data here that interests us, and that is the differences. The difference between the fridge and the room temperature for each of the different types of peppers. And so we formulate this hypothesis test in this way. Our null hypothesis says that the mean difference is 0. And the alternative hypothesis says the mean difference is not 0. So we're not going to calculate the average for the fridge and the average for the room temperature and look at the difference. No. Instead, we're going to get the difference for each item and see if the difference is 0. In this way, we will only ever compare one colour of pepper with the same colour of pepper stored at the other set of conditions. So any differences between the peppers will not have an impact on our results. So our differences are listed there, 4.7, 3.1, 4.2 and 8.4. Those are the data that we will use to perform the test. So there's a single population of differences, and we're interested to know if the mean of that population is 0 or some other number. So we calculate the sample statistics working with those differences. The x bar is 5.1, the mean difference. The standard deviation is 2.3, the standard deviation of the differences. N equals 4, the number of differences, and of course the degrees of freedom equals 3, n minus 1. So we calculate the t statistic using the one sample t-test that was presented earlier in chapter 5, and we substitute those values into the formula for t and we get 4.43. And as always, we leave that calculated value there while we go and look in the tables for 3 degrees of freedom and the appropriate critical value to provide us with the value for a two-tailed test. So in the tables of the t-distribution, with 3 degrees of freedom, we look under the 2.5% heading. 2.5% in both the left and right tails means 5% in the rejection region comprising both tails. So 3.182 is the critical value. The calculated value is 4.43. This is more extreme than the critical value, so the calculated value of the test statistic falls into the rejection region. So we reject the null hypothesis that the mean difference is 0 in favour of the alternative. The mean difference is not 0. In fact, the peppers stored in the fridge have higher vitamin C concentration than peppers stored at room temperature. So that's an example of a paired t-test. We're comparing two populations, but in fact, because the data are paired, we just have a single set of differences. And when it's possible to take that approach should be taken. Sometimes it's not possible to pair the data. So we're now going to go ahead and look at a two-sample t-test, where there are two samples from two different populations that don't lend themselves to pairing, and where we want to test the null hypothesis that the means are equal as opposed to not being equal. The test statistic that we use here is a t-statistic, and the t-statistic is x1 bar minus x2 bar, so it's the difference between the sample means, divided by the square root of s squared over n1 plus s squared over n2, and that quantity in the denominator is the standard error of the difference between two sample means. And you will notice that s squared is used twice. We are assuming that the two populations have a common standard deviation. So we use a pooled variance estimate from all of the data to calculate that common standard deviation before proceeding with the test. This statistic compares two populations. If we ever need to compare more than two populations, then there are procedures presented in Chapter 7 for doing that. One way ANOVA is a way of comparing more than two populations. So our example that we're looking at here has to do with the quality of groundwater. The biological oxygen demand is a measure of the level of pollution in groundwater, and when groundwater is passed through a treatment plant, the biological oxygen demand should reduce. So what we have here are a number of measurements of biological oxygen demand taken from the influent and the effluent of a groundwater treatment tank. We want to use a two-sample t-test to investigate whether the effluent measurements are lower. This would confirm that the groundwater treatment tank is having a positive effect on the quality of the water. So we have there three values for the influent, and we have a greater number of values for the effluent. The sample sizes don't have to be the same. And again, in particular, you will notice these values are not paired. It is not possible to pair the values because the influent and effluent values, there's not a one-to-one correspondence between them. So we proceed as follows. We lay out the test by saying the null hypothesis states that the two means are equal, the influent and effluent. mu1 equals mu2 is our null hypothesis. Our alternative hypothesis is that mu1 is greater than mu2, so the influent measurements are higher, and therefore the effluent measurements are lower. So n1 equals 3, and n2 equals 8. S1 is 12.7, and S2 is 6.4, and x1 bar is 205.33, and x2 bar is 175.88. So we will begin by calculating S, the assumed equal standard deviation, the common standard deviation of both influent and effluent, by combining together the estimates of standard deviation from these two samples. So we apply formula 4.9 and we calculate the pooled variance estimate as 67.73, and that's based on 9 degrees of freedom, n1 plus n2 minus 1 minus 1, n1 plus n2 minus 2. Now, we then substitute the value of S and the values for the mean and the sample sizes into the two-sample t-test formula. And having substituted and calculated the value of t, we get 5.29. And as always, we leave that figure there while we then go to the tables and see what is the critical value. So going to the t-tables with 9 degrees of freedom and looking under the 5% heading, because we have here a one-tailed test, and so we want to have 5% in a single tail. So with 9 degrees of freedom, the 5% point of the t-distribution is 1.833. Our calculated value of t is 5.29, which is more extreme than 1.833. So the calculated value, 5.29, is in the rejection region. the p-value is less than 5%, the data assert that the means are not equal, and rather mu1 is greater than mu2. In other words, the effluent measurements are lower, which is what we want to be the case. Okay, so here we have presented in this section two different ways of comparing two populations, and where it is possible, use paired data, so that any differences between the objects that are selected will not have an impact on the calculations. If it's not possible to pair the data, then we have available to us a two-sample t-test. And you can read more about this in the textbook in section 5C, difference between means.